What's up, crammers? Welcome to the linear algebra crash course, which is going to go through a full semester of linear algebra. And I'm kind of making this because my teacher did not really explain or show what was going on, so I wanted to do that in this video. So the first thing we're going to look at is just a few basics. Now, these are going to be elementary row operations and matrix multiplication, which is basically what linear algebra is. So here are our elementary row operations: swaps, multiplying, and adding one row with another row. So swapping rows, pretty simple. You're just changing the two rows. Multiplying, you can multiply an entire row by some number. And so we want to get this 5 to become a 1. So we can just multiply it by 1/5, and that becomes 1. We can say this is row 1, this is row 2, and this is row 3. And then we can say that row 1 is going to be equal to 1/5 of row 1. And then finally, we can add a row with another row, which is going to be used quite often. Now, how do we get this to become 1, 0, 0? We can add it by this, what's called a pivot point. We can multiply this bottom row by -8. We can say row 1 is equal to -8 times row 3 plus row 1 again. And a way I like to show work, and just to help myself, is I like to write it on top of the next matrix. So 0 times -8 is 0, 1 times -8 is -8. And then I can write out all of this, which is unchanged. And then -8 plus 8 is going to be 0. What we're trying to do here is to get it into this form, which is called reduced row echelon form. And a strategy you want to do is to get it column by column. So I want to get 1, 0, and 0 correct first, and I'll move on to the next column, 0, 1, 0, and then 0, 0, 1. And we can use these pivot points to our advantage here. Real quickly, I'm going to go through some matrix multiplication. Now, I like to do some hand motions here. So I'm thinking flat, and then it dips down, and just kind of keep this motion in mind. So what does that look like? Well, that's going to be 1 times 5 is 5 plus 2 times 7, which is 14. And then I can move on to the next column. So 1 times 6 is 6. 2 times 8 is 16. And we run out of columns on this side, so let's move down one row. 3 times 5 is 15. 4 times 7 is 28. 3 times 6 is 18. 4 times 8 is 32. So let's say I have something like this. I can rewrite this as a matrix 1, 2, with a bar here, 0, and 2, 2, 1. And the reason is, if I take this 1, 2, 2, 2, and I multiply by x and y, and we do that same motion here, we're going to get x plus 2y, 2x plus 2y, which is just this right here. Now, I'm going to spend quite a bit of time just going through linear independence and span, since they are crucial topics for what's later on. Essentially, if we get something like this, we can rewrite this as x plus 2y equals 2, and then, well, 0x plus 0y equals 0, or 0 equals 0, which is true. Now, we want to show it as an xy matrix, since that's kind of what we're multiplying here to get this. So we can rewrite it as x equals to 2 minus 2y, y is just equal to y. Y can be anything it wants to. Now we can rewrite this as y times -2 and 1, since we have y's in both of these, plus just constants. And what we notice about these equations is that x is dependent on y, because there's a y in the x. So that means this is linearly dependent. I can write this as the span of -2, 1, which I'll get into in a little bit. For now, I want to rewrite this top matrix as x times 0, 1 plus y times 2, 0. So what linear independence means is that there's only one linear combination that you'll get the 0, 0 vector, or the trivial solution. And instead of explaining what linear combinations are, I'm just going to make some right now. So x equals -2, y equals 1. That's one linear combination. X equals -4, y equals 2. That's another linear combination. Now, why did I choose these specifically? Well, if we plug in these numbers for x and y, what we'll get is -2, 0. -2 times 1 is -2, plus 2, 0. Now, what do we get when we add these two? We get 0, 0. Okay, so that's one way to get the 0, 0 vector. Now, let's try this other one. X equals -4. So -4 times 1 is -4, and 0 is the same, plus 2 times 2 is going to be 4. And we'll notice that also equals 0, 0. So this is not linearly independent, because we just found two ways to get the 0, 0 vector. And going back to that span -2, 1 thing, if we look above, we have x equals 2 minus 2y, which is essentially a line. And so what the span is saying is, if you multiply any number with that vector, -2, 1, you'll get some point on the line x equals 2 minus 2y. If you have two independent vectors, they might look something like this. Essentially, if you combine the two with any linear combinations, you'll be able to kind of create a plane. And this plane is going to spread in two different dimensions, which means that it spans R2, or 2 dimensions. I'm actually going to show some examples visually here. So once again, we have two vectors, and you're going to be able to kind of make this plane, and so that's going to span 2 dimensions. Now let's try a 3-dimensional one. What happens now? I'm just going to draw 2 like that. Well, now we're going to get a plane. You aren't able to unlock that 3rd dimension to go up and down, essentially. And so it is impossible to span R3 with 2 vectors. But if we have 3 linearly independent vectors, you'll notice that it's going to make like a cube type of shape, infinite size, and you're able to reach all 3 dimensions. Now let's get into some numerical and arithmetic examples here. So is this linearly independent? We can test it, or we can just look. Now 3x3 vectors and higher, it's not as easy to tell, but here we see that we have 1, 1, 1 and 2, 2, 2 here. And if we multiply the first vector by 2, well, we're going to get the second vector. So essentially we're looking at 2 vectors like this. And so that means we can just cross one of them out. And so that means we only have 2 vectors. So it only spans R2, and it is not linearly independent. The way to prove it is to set it equal to the 0 vector like this. I want to get rid of these bottom 2 ones to get zeros. So I'm going to multiply the top one by -1. So that makes these negative. These are going to stay the same. -1 plus 1 is 0. -2 plus 0 is 0. -1 plus 2 is 1. And I'm just going to continue with this. And what you'll notice now is that we don't have a pivot here. We don't have a 1 or any number, in fact. Which means this is going to get kind of dicey, because what's going to happen is if I multiply this bottom row by 1/2, we're going to get 2 rows like this. And when I try to clean up this part, 0, 0, 0, because 1 minus 1 is 0, and 0, 0, 1, that stays the same. And this essentially means x plus 2y equals 0. 0 equals 0, so y equals y in this case, and z equals 0. So this, in fact, is linearly dependent. First rewriting x equal to -2y. We could rewrite this as a span of -2, 1, and 0. Now let's check if vectors span a certain dimension. So in this case, we have 2 vectors. We want to see if it spans R2. So what we can do is say, just put in variables a and b. So we're going to set the solution to a and b. And this is going to be the exact same process as we did for linear independence, trying to reduce it as much as possible. Just doing the steps here, making sure you're getting this -a here and -b plus a. And we get this answer. And so this means x is equal to 2a minus b, y equals b minus a. Now we could plug it back into these vectors here. Again, x times 1, 1 plus y times 1, 2, like so. Just multiplying it out, we get this. And when we add these together, we'll notice this b is going to go away. -a plus 2a is going to be just a. And then here, 2a minus 2a, that's gone. -b plus 2b is b, and we once again get a and b. So these vectors do span R2, and that is how you prove it. And just here are some other examples here. So when we have a 3 by 2, so row by column matrix here, this will span R2. Remember, it won't span R3 because it's only 2 vectors. But this is actually linearly independent because we have a pivot point, or in this case a 1, in every column. Like if we write x, y in here, there's no z at the end here. So it's just going to be x equals 0, y equals 0, and that's it. And then for the second one, this one is not linearly independent, and this one does span R2. Once again, x equals 0, y equals 0, but we still have this z component that's somewhere here. That's just going to be 0, 0, 0 here. So z equals z. Now moving on to linear transformations. Now visually, linear transformations you could think of in computer graphics and video games. You're looking at 3D objects like a cube, but you're looking at it on a 2D screen. And so you can use linear transformations to kind of create that so-called illusion, I guess you could say. And so there's 3 types of linear transformations here that I want to go over. First one is taking a smaller dimensional matrix to a larger dimensional one. Next is just from one dimension to the same dimension. And finally, taking a larger dimension to a smaller, so like 3D to 2D. So let's start with the first one, smaller dimension to higher dimension. Now, if we think about this, we have a 2D, let's just say this line, say this is, 1D. How do we get this to become projected onto a 2D plane? Well, we're gonna need to add more information. And as such, as an example here, we're given two pieces of information. We're given that T12 equals this and T34 equals this matrix. So a property of linear transformations here is that you can kind of split them up, and I'll kind of show you how. What we want to do is say T10, so getting rid of that 2 there, and then adding 2T times 0, 1. And all I did here was, it was originally 0, 2, and I moved 2 to the outside. And then we could do the same splitting action with this 3 and 4. So I want to get 1, 0 and 0, 1. So I can first split it up and then get rid of move the 3 to the outside, like so. And then similarly with the 4, and that'll equal this matrix. So what do we do with this? We can multiply this entire thing by -2. And so just putting it down here, we'll get -2t minus 4t equals all of this times -2. And you'll notice now we have a 4t minus 4t, cross that out, and we'll get T10 equals -10 and 3. And now's a good time to go back to that identity matrix thing. This is 1, 0, 0, 1. If you multiply this matrix by any matrix, let's say this for example, you're going to get the same matrix. Now we can use that to our advantage. Now we can say that some matrix T times 1, 0, 0, 1, the identity matrix, is going to be equal to something. And that's how we can find what T is. So now that we have this answer here, we can plug T10 into one of these equations. I'm going to plug it back into this one here. So right now I'm just rewriting the equation at the top, but instead of putting T10, I'm going to put in the answer that we found. So now let's just subtract this matrix to the other side, and we get something like this. And then we can see if we divide everything by 2 to get our T equals 0, 1, we get our nice answer of 2, 7, -2. We have T10 and T01. If we combine it back together, we get T10, equals, and then we can combine the answers together as well to get this. So this right here is our transformation matrix. And I just got this from here, this from here. Now our next example is going to be from a higher dimension, like an object, into, let's say, a computer screen. This is the easiest version of it. All you do is you just multiply. So -1 times 2 is -2, -4 times 1 is -4, -5 times 3 is -15, 1 times 3 is 3, and that's it. And once again, essentially what we're saying is this is our transformation matrix, these are the values, and this is what we get in return. Now we're going to look at two-dimensional transformations transforming to other two-dimensional spaces. This is what you're going to probably be using the most, and there's a lot to go over, but there's a few good things to remember. The first thing is how to visualize this. So I've kind of drawn it out in color here, but you want to think of two vectors. Here, if we want to rotate by 90 degrees, you can use this equation right here. This is a good one to remember. Cosine, negative sine, sine, cosine. Cosine, negative sine, sine, cosine. And for something like this, in the bottom left here, I'm going to redo this example here. So we have 1, 1, and we want to find what it is with the reflection on the x-axis. So that just means that we're changing the y-axis and making it negative. So that's going to be 1 and -1 here. Now we have to find a matrix that we can multiply something t times 1, 1, which will give us 1, -1. So how do we do that? So we have our identity matrix, which doesn't do anything when you multiply, and we could start fiddling with this. Now, what happens if we change the negative on this first one? Well, then you're going to be multiplying this with this one right here, which is the x. So you're making the x negative. So okay, then let's try this other one. Let's make that one negative. So now when you multiply it by 1, 1, you'll see that you get 1 and then -1 when you multiply it. And I probably should have mentioned this earlier. Matrix multiplication has to be in a specific order, so you can't just flip them like this. 1 to 1 and onto, or injective, some might call it. Essentially what you want to look for is T, the transformation matrix, is it linearly independent? And here's a visual. So this is not 1 to 1 because you have 3 points mapping to a single other point on the other side. But here, each point is mapping to another singular point in the transformed space. And for onto, well, you want to see if T spans R to the n. So once again, 1 to 1, see if it's linearly independent. Do the 0, 0 thing. If it's onto, set it to equal to A and B. And visually, let's say Rn is R2 and Rm is R3. Well, then they're not spanning the same dimensions, so that's not onto, but this one is onto because it's from 2 dimensions to 2 dimensions again. Now we're going to cover a few more background things, such as transpose here, where the rows just become columns, so you can just imagine this motion, or 1, 2 equals 1, 2. And I also want to look at inverse. When you take the inverse and you multiply it by the non-inverse, you get the identity matrix 1, 0, 0, 1. So here's another good thing to memorize. 2 by 2 inverses. The way to do a 2 by 2 inverse is you take this diagonal here, you multiply it. So 1 times 4 is 4. Then you take this diagonal here, 2 times 3 is 6, and you subtract it with the first diagonal. So 4 minus 6, and then you stick a 1 at the top. In this case, it's going to be 1 over negative 2. And then you want to flip around the matrix a little bit. So your first and fourth numbers are going to swap. So it's just going to be 4 and 1. And then the second and third numbers are just going to turn into the negatives of each other. Here is a kind of a proof of that. So I stuck the negative 1/2 on the outside, did a multiplication, and yep, I got the identity matrix. So that's a good thing to remember. Now, who cares about this? Well, how do we find what A is? We can use the power of identity matrices and inverse matrices. So what we know is from above here is that if we multiply the matrix with the inverse matrix, and here, yes, you can kind of flip them around, we get the identity matrix. And when you multiply the identity matrix by A, it's just equal to A. So what we can do is we could stick an inverse right here. Make sure that it is closest to the matrix that you're making the inverse. Make sure it is not on the other side of A. And since we're doing it on this side, we obviously have to multiply it on the other side. Now what we can do is cross this out and we get A equals something, which I don't really want to solve this. So 2 by 2 inverses, they're decently nice, like you can memorize, it's memorizable. But when you get to higher dimensions like 3 by 3s, you can't really memorize steps you need to do. So what you're going to do is you're going to reduce it to reduced row echelon form, just like before, except on this side, you are setting the matrix that you want to inverse equal to the identity matrix. So essentially, you're just like kind of flipping sides here. And your answer here is just going to be the inverse of this. All right, so what if we have multiple operations in a row and we want to see how we could get from the first one to the last one? And this also works with linear transformations. So here's an interesting thing. We're going to create a matrix for each step that we can multiply to get the next step. And then with each matrix, we're going to flip the order and multiply them that way. I'll show you with this example. So how do we get from this matrix to this next one? Well, we're multiplying the first row by 2. So just make that into 2, and the rest is the identity matrix. Next, it looks like we're doing a row swap with the first and second. And so to swap rows, well, you can just swap the rows in the identity matrix. And then this one's slightly more confusing. We're adding 5 from the third row to the first row. And so we could write this as 1, 0, and then 5 from the third row, and then the rest is the same. If we multiply all of these matrices together, we will not get the right answer. You actually have to switch the order. So this is actually why I like to do it in backwards order when I'm solving these questions. I like to go look at this first, and then from the second to the third, and then first to second. So I don't have to rewrite these. And as you can see, we get the same answer because it's just the identity matrix, so you're going to get the same answer here. I should also mention undoing row operations. So if you want to undo a row swap, well, it's going to be the same as the row swap. If you want to undo multiplication, let's say you want to multiply 5 times something, well then to get it back to 1, you can multiply it by 1/5. And then for the addition of adding one row to another row, you could just subtract. So in this case right here, it's just going to be 1, 0, and -5. So now we're going to go into determinants, and I don't really want to explain this. I'll link a 3 blue 1 brown video, but it's essentially giving a value for like scaling of linear transformations and whatnot. And that essentially means that you're going to get a numerical value as opposed to a matrix. It's going to be a scalar. You want to alternate pluses and minuses. So I have +1, -2, +3, -4, +5, -6. Let's take this top row here. Start with 1. 1 is in 1 row and 1 column, so we're not going to touch those at all. We're going to be dealing with the square that's on the opposite side here. And so we're going to put that into a matrix like this. Same with 2 and 3, that's kind of what I did there. I've dropped the negatives because I think this is a better way to think about it. You're turning it into 2 by 2 determinants, and the way to solve 2 by 2 determinants is kind of how we did the inverse, where we take this diagonal, multiply them, subtract them by this diagonal. So that's why memorizing the inverse process won't be too difficult, since you also have to memorize determinants. Now, what happens if you have a 5 by 5 determinant? Because here we made a 3 by 3 into 3 2 by 2s. If you have a 4 by 4, then that's going to become 3 by 3s, which then become 2 by 2s. And if you get bigger matrices, then it's going to get way too complicated. So what you could do is turn it into row echelon forms. No, not reduced row echelon form, but just row echelon form, where you have zeros down here, but you can just ignore this top part here. And the reason is because when you're doing these operations and you're multiplying, like this 2 by 2 part, when you have the zeros, a lot of it will just turn into 0. And so a nice property is if you get the staircase diagonal here, you can just multiply each number in the staircase and get your determinant. Now remember, when you're doing row operations to get this, swapping rows and multiplication changes the determinant. When you swap a row, you have to make sure to add a negative to your determinant. So let's say I swapped 2 rows. Well, then I added a negative and then put another negative, so that just becomes positive. And with multiplication, you have to multiply the determinant with what you multiplied the row. So let's say I multiplied this row by 4. Well, then you're going to have to multiply the determinant by 4 as well. So now let's move on to vector spaces. Here's the 10 rules. I usually don't really care about them, and that's because I like to memorize subspace rules, which are vectors in the vector space. And so here are the 3 rules, or at least 2 rules I like to memorize. One has the 0 vector. It's closed under vector addition and is closed under scalar multiplication. So to prove that these vectors are a subspace, you just show that S is a span. And to disprove, you try to violate one of these 2 rules above. So let's do this example. Let S equal to xyz such that x plus 2y minus z equals 0. Essentially, we can think of this as having y equals y and z equals z here. It's just not shown. So let's set x equal to something. That's going to be negative 2y plus z. And then we have these remaining 2, which means we're going to have y times negative 2, 1, 0 plus z times 1, 0, 1. And we can write this as span of negative 2, 1, 0, 1, 0, 1. And since we have this span, it exists, this is a subspace. And while we haven't gotten into basis yet, it's good to know that these 2 vectors here are a basis for S. Now, is this a subspace or not? We're going to be using the rule violation of scalar multiplication in this example. Let's find something that is true here. X plus y plus z equals 1. Well, if x equals 1, y equals 1, and z equals negative 1, well, 1 plus 1 minus 1 is equal to 1. So that is correct. However, we can rewrite it like this, 1, 1, negative 1. We multiply it by 2. Just like that. Now we get 2, 2, negative 2. But when we're adding 2 plus 2 minus 2, that gives us 2, which is not equal to 1. So this disproves that this is a subspace. Now here's another example, x, y, z equals 0. We know that if x equals 0, y equals 1, and z equals 1, that just equals 0. And we also know if we have x equals 1, but y and z equals 0, well then it still equals 0. Now, here's the issue with this. If we write these out as vectors and we add them, you'll see that we get 1, 1, 1. And 1, 1, 1 equals 1, which is not equal to 0. And so this is disproving the subspace by addition. And I'll just introduce basis here briefly. So now think of the word basis, kind of like it's a base of whatever thing you're trying to describe here. And so when we're looking at just a normal Cartesian coordinate plane, we're counting by 1 for each step. The basis is going to be these 2 vectors, which this one's at 1 and this one's at 1. That's just how to describe it. And so when you're trying to see the basis of a space, you want to see if it's both linearly independent and it spans R to the n. So essentially it's square. And that's why like this here checks both of those boxes. But you have to remember, this is the basis for a space of, let's say, like R to the n, because we're going to look at examples that don't exactly follow this rule of basis. So if you weren't already confused enough, let's go through more things that can be described and found in the same way. Null spaces. Just look for linear independence. Same thing, set it equal to 0. But your answer here is going to be the span vectors, and I'll kind of show you what I mean there. So this example here has been reduced all the way. We'll get this span vector, and that's your null space. We can call this null A. And we can say that -2, -1, 1 is a basis for null A. Now watch out, don't get confused with column space, which you also look for linear independence, but the answer is slightly different. You're looking at the columns that have pivots. So we can just go back to the original matrix, which is something like this, and take those vectors, the span of those vectors, and this is going to be equal to column A, or col A. And once again, these two vectors inside are a basis for column A. And here's some more stupid definitions. Nullity is the dimension of null A, and rank is the dimension of col A. So in this case, the rank is 2. And in this case, the nullity is 1. So if you thought that was abstract, well, welcome to abstract vector spaces. I'm going to go through two different types here. The first one is a vector space of a bunch of different dimensional matrices. In this case, it's 2x2s. And so we want to see if these matrices are linearly independent. Now, just like before, we can write this, if we say this is A, B, and C, we could write this as x times A, y times B plus z times C. And we could set it equal to, once again, the 0 vector. But what is the 0 vector? Well, in this case, it's going to be 0, 0, 0, 0. So we can take the first number from each matrix. So that's going to be 1, 1, and 1. Then take the next number, 1, 4, and 6. The last one, 3, 2, and 1. Do the whole reduced row echelon thing again, and you'll get some answer, and you can figure out if it's linearly independent or not. And once again, to check if it is, say x is 2, y is 1, z is 2, we can then multiply our original matrices here by 2, 1, and 2, and when you add all of them up, see what you get. And here's the second type of abstract vector space I want to talk about here, which is degrees of polynomials, in this case second degrees. And so an example question would be to find that S is a subspace. Now we're given that P of X is in P2. This essentially means you could say that P of X is equal to some number A x squared plus some number B x plus some number C. That right there is a second degree polynomial. Now let's solve these and just plug these in. So P of 1, just substitute X for 1. That's going to be A plus B plus C. This is not inverse, this is the derivative of P3. The derivative of this, if you haven't done calculus, I'll just state it, it's going to be 2ax plus b. And so plugging in 3, we're just going to get 6a plus b, and setting all this equal to 0 here. Now let's just solve for c, perhaps, because it looks nice. We'll get -7a minus 7b. Now we have this c. We could plug it back in to this p of x thing here. And now we could say that P of X equals AX squared plus BX minus 7A minus 2B. Now let's separate the A's and B's, and we'll get something like this. Now remember, A and B are just constants. They can be any constants, and so they could have infinite combinations. So we could say it is the span of x squared minus 7 comma x minus 2. And since we have a span, we've just proved that S is a subspace. So once again, we are revisiting basis. Normally we have, coordinate systems such as this one. And let's say we want to change that coordinate system. We want to transform it into something like this. Essentially, if you want to represent something in a different coordinate space, you want to change the basis. Essentially, by changing the basis, you're changing how the coordinate system is set up. And so for this equation, you're given an x, and you're trying to find how to represent that x in your new basis system. Now, I want to demonstrate some more slightly complicated examples just because you could plug this equation in for literally like most questions. Now, we have b, which is this set, c, which is this set, x of b, which is this, and we want to find x of c. So from the above equation, we can kind of just plug it in as well. And so we get this where we don't know what our x vector is, and we want to solve for it. But how do we get x by itself? Once again, you can have multiply an inverse, and you can multiply on both sides. Just like that, I multiplied the inverse with this, which became the identity, so I got rid of it. And that is your answer for x. And now that you know what x is, and you know what c is, you can find what x of c is in this right here. just like so. And then here's an interesting one. We want to find vectors b1 and b2. Another way of saying v1 and v2. So we can see that these are our x vectors here. And so if we try plugging it into the equation here, so we can shove all of this into our equation once again. So I'm going to do the right side first. We know b, our basis, is b1 and b2. So that's the inverse of it times 1, 2, which is our x here. And that is equal to, it says 3, 4. And then we have a second one as well. 2, negative 1 from up here is equal to the same vectors times 4, 3. Now let's just combine our two equations now. So this went into there, and this went into there. We now have the inverse of b1, b2, so let's just get the non-inverse. So when we multiply this by b1, b2, just non-inverse, that goes away, and then we have to multiply it on the other side as well. And then we also have to multiply this by its inverse and multiply it on this side, like so, get rid of that. And this is our answer right here. And although I went through it pretty fast, it's just a bunch of the matrix manipulation stuff that we did earlier. All right, now let's try to do something interesting. Let's reflect a point across some line, y equals negative 3x, which kind of looks like this. So originally, your xy plane, you're going to have y equals 0 as your x-axis and x equals 0 as your y-axis. But we're going to be changing y equals 0 to y equals negative 3x. And another thing to note is that a linear transformation for a reflection across y equals 0 is this matrix right here, which we did earlier. And so kind of a visual process of this. What I like to do in these cases is I'll literally have my graph out and I will flip the page. And so if this was my y equals 0, I will flip this whole page to make this y equals negative 3x. And I've kind of tried color coding it as best as I could here. The darker red and green are the originals, and the lighter colors are after kind of the transformation here. And so you'll notice that y equals 0 moved to y equals negative 3x. And this green line, the way to figure that one out is just, it's going to be the negative inverse of y equals negative 3x. And we also want to note the direction. So usually we count up this way. We count to the right to increase x, and we count up to increase y. So when we flip our thing here, and I'm actually going to flip this entire iPad here, we notice that our arrows are now pointing kind of left and up, and then here it's going left and down. So if I were to write that, draw that here, this original one was going to the left and up, and this one was going left and down. And that's important because now we can write our matrix versions of this. So we know this is negative 3 and this is negative 1. So that means you're moving negative 3 to the left and then going down negative 1. That's that matrix. And then for this one, you're moving to the left by negative 1 and you're increasing by 3. So it's going to be negative 1 and 3. And so while we had 1, 0, 0, 1 originally, our new basis vectors are going to be negative 1, 3 and negative 3, negative 1. Now the way we do this is by looking back at our original formula, which I'm writing out here. Now we notice this part right here, and this corresponds just exactly to this part of the equation. And exactly what we're trying to find, which is our new vectors in this new basis. And we also want to remember that when we're doing a bunch of operations, we have to multiply the matrices in backwards order. That's why our starting thing is going to be last, our reflections in the middle, and our conversion back to the original coordinates, or just the non-inverse version, is going to be the first thing we multiply. Welcome to Eigen Stuff. Vectors, values, spaces, you name it. Here is once again another formula you want to memorize. I mentioned a couple formulas you wanted to memorize, but there's not that many. So here, as we can see, we have A, which is a square n by n matrix, and then we have X, which is our eigenvectors, which we'll get into in a bit, is equal to an eigenvalue times the eigenvector. So visually what this is when you have a linear transformation, you can think of kind of all the vectors moving around and shifting. But at times, there are some vectors that don't go off their span. If you remember what span is, let's say this vector, it's spanning whatever this line is here. Usually in a linear transformation, if we were to rotate it or something, it would get knocked off its span, which was originally here. But in some cases, some vectors will stay on their span, but they will either increase or decrease in their magnitude. And so their magnitude is the eigenvalue, and the vectors themselves are the eigenvectors. So here's just a visualization of what this formula would look like with matrices and stuff. So let's move on to an example. We have to find the eigenvalues, eigenvectors, and eigenspaces for this matrix right here. Now there is a formula to memorize right here, which is the determinant of the identity matrix times a lambda matrix, which we'll get into, minus A equals 0. So instead of thinking about this formula, what I like to do is I just like to think of the process. So here's my process. I take A and I just flip all the negatives and positive symbols. So I make it negative A, and then add a lambda to the diagonal values. I'll have a lambda here, and I'll be adding 13 since that is the opposite of negative 13. So 6 will become negative 6. Negative 45 will become 45, and then I want to add another lambda to this diagonal, be negative 20. And so that determinant will equal 0. Further expansion on this equation will give you this, which you can solve for lambda, like so. So then lambda equals 2 and 5. So now we can plug in lambda into our original matrix A here. So when lambda equals to 2, this is how I like to write it, we have 15, negative 6, 45, and then 2 minus 20 is negative 18. And we want to set this equal to 0. So if your questions are nice, you'll notice that this row and this row are just scalar multiples of each other. If I multiply the first row by 3, then the bottom row will be the first row times 3. So I'm just going to right away make that into zeros. And then I'm going to try to simplify this as much as I can. Dividing everything by 3, we'll get 5, negative 2, and 0. So then I can write this as 5x minus 2y equals 0. So y equals 2/5 times x. Now, I want to get a vector that kind of represents this equation here. I want to get integers in my vector. I don't want to deal with fractions. What I'm going to do is I'm going to set x equal to 5, because if we have 5 here, we can knock out the 5 in the denominator, and we will get y equals to 2. And so our eigenvector is going to be 5, 2 for the eigenvalue of 2. And in a similar fashion, we can do the same thing when the eigenvalue is equal to 5, just plugging it into that matrix once again. Turns out this one is a little bit nicer. Y equals 3x. If x equals 1, then y equals 3. And finally, I guess we want to find the eigenspace. I'm just going to do it for this example right here. All we have to do is say this is the span of that vector, and we can say, since this was associated with lambda equals 2, the eigenvalue of 2, we can say E2 equals the span. That's about it. Now let's expand on this and go into diagonalization, which is a different way of writing matrix A. This is our A here, to allow you to do different types of operations, such as this one where we want to find A to the nth power. This is the same example here. I'm just going to take from what we've got. Let's see, I started with 2 and then I went to 5. So 5, 2, and 1, 3. And then for our eigenvalues, we're just going to plug in the numbers that we got for our eigenvalues into the diagonals, making sure that you're doing it in the correct order. So I started with the eigenvector that was associated with the eigenvalue of 2. So I'm going to make sure to put 2 there. And then we'll have zeros here. And then the other eigenvalue was 5. And then I'll just put in the inverse. And you can check, if you multiply this out, you should be getting this matrix. Now, if I want to find this matrix to the nth power, then I can just, in my eigenvalues matrix, I could just set it to the n. Now remember, when you're multiplying this, 2 times 2 to the n is not equal to 4 to the n. Let's go into another application of eigenvalues and eigenvectors, which is in population modeling and just modeling a lot of things in general. In this example here, we have some species that can reproduce by itself. So here I've abbreviated A for adults and J for juveniles, or I guess kids you could call them. And the rules of this population is that every single year the juveniles will grow up into adults. And here are our percentages of how many survive. 40% of adults will reproduce and create a juvenile. 20% of juveniles will survive to become adults, and 70% of adults will continue living to the next year. So what we want to try to find is, in the long run, what's going to happen to this population. Now we want to find a matrix that can represent this, and is going to represent the number of years. So let's say the next year is going to be equal to something. We need to multiply something times the original population for that year. So to set it up, remember that the top row is going to be multiplied by Jan and An to get the resulting top row, which is juveniles, and same thing for adults, which will be the bottom row. If we're looking at the top one here, for juveniles specifically, juveniles cannot create themselves, so that's going to be 0. And then for the second one, we're going to be multiplying it with the adults, but it's going to result in some number that is going to equate to juveniles. That was a lot of random word garbage, but essentially how much of the adult population is going to create juveniles. And in this case, we have 40%, so I'm going to multiply it by 0.4. Now we're getting into the adult territory here. So how many of the juveniles turn into adults? Well, 20% here, so we're going to put a 0.2 here. And then 70% survive, so just a 0.7 there. And that is how you set up the matrix. Just again, think about this whole multiplying motion. So now you just have to get the eigenvalues. Once again, this is where I did not appreciate the no calculator rule, but I'll just do the setup here. So we have lambda minus zeros, whatever, turn into negative 0.4, negative 0.2, and then lambda minus 0.7. And then we want to find when that equals 0, the determinant of that. For this example, we're going to get negative 0.8 and positive 0.1 here. Equals to 0 means our lambda is going to be equal to negative 0.1 and 0.8. Now let's put it into this equation. So for any n number of years, this is going to be equal to, remember what we had before. We had like x times some vector plus y times, some vector. We're going to do pretty much the same thing here because we don't know what our x and y is. That's to be set for later. So we'll have x here, and then we're going to be multiplying it with our first eigenvalue to the nth power, just like what we did with diagonalization. Now in my example here, I just want to see what happens in the long run, but if you want specific values for specific years, the v1 and v2 are going to be the corresponding eigenvectors. Just remember that. Now the reason why these don't really matter, and it's just going to be based off of your eigenvalues, because if you look at when n goes to infinity, what happens to negative 0.1 when it's raised to the infinity? Well, this will essentially just go to 0. And then when you have 0.8 to the infinity, well, if you're thinking of 4/5, another way to represent it, to the infinity, your numbers are going to be getting smaller and smaller because your denominator is larger. And eventually, it'll also go to 0. Which means this population is going to go extinct. And I mean, you can kind of just figure that out by looking at the numbers here. If only 20% of the juveniles are becoming adults and only 40% of adults are reproducing, it's not looking real good. So we say goodbye to the eigen stuff and move on to the last section. Now just here's a bunch of properties that I wrote down. When you dot vectors, it's essentially multiplying A transpose with B. And it's an interesting way of thinking about it. And I'll write down an example here. I want to dot these two vectors. I can then write it like this, which will be equal to 1 times 1 is 1 plus 2 times 2 is 4, which is just 5. Now, the way I like to think about it is just with these two vectors, I'm going to write it out here again. Just look at it this way, line by line here. So 1 times 1 is 1. 2 times 2 is 4. I think that's a lot easier rather than having to rewrite it with the transpose and then trying to figure out this whole matrix multiplication thing. Another concept is orthogonality, which is just a fancy way of saying perpendicular. So A and B are orthogonal if and only if A dot B equals 0. And so in this example here, if we do the dot product here, and I don't know why I'm writing that, 1 times 2 is 2 plus 1 times negative 1 is negative 1 plus 1 times negative 1 is negative 1, and that equals 0. So that checks out, and these two are orthogonal. For an orthogonal set, let's just say 5 different vectors in some set of vectors, then any of the two vectors that you choose when you dot them will have to equal 0. And sometimes they might ask you for orthonormal, or any normal vector, which is essentially a vector that is of length 1. And to get that, you divide your vector by the square root of that vector dotted with itself. Here's another ortho type thing. This one is in orthogonal complement, so note the wording there. And this is where the subspace of the vectors are orthogonal to the vectors in S here. And so we're going to do an example, which is this one right here. All you have to remember is to flip all of these from columns to rows. So essentially taking the transpose. So this 1, 1, 1, 1, and it would just look like that, and you can reduce that to your heart's content. But essentially what this is looking at is like you're going to have three different vectors, let's just say like this, and you want to find the span. So it's going to, look like something like this. You want to find the span of vectors that are perpendicular to all of these other vectors. This is a horrible drawing. Oh my god. Like you want to find these vectors right there. Here's two more things to remember. I'm not going to go through the derivation of this. We have complements and projections. So the way you read this is complement of B onto A and projection of B onto A. I know, it's really weird. What it is you have these two vectors A and B here, and you want to project the B vector onto the A vector. We can just draw a straight line down, and it would be this vector right here. And then to find the vector perpendicular to it, which is this thing right here, we can use the B vector subtracted with the projection of B onto A. And so the formula for the projection is right here, A dot B over A dot A times A. And that will give you a vector because you're multiplying, this will turn into a scalar, but you're multiplying it with a vector, so it'll be a vector. Thing to note, with the complement, which is the length of the projection, which is going to be a scalar, you have A dot B over the magnitude of A. And you're not multiplying it by any vector, so it's just going to be a number. And we're going to go through an example in a second here, but for a span, we can call it W here. For the projection of some y onto a span, or let's say in this case, a two-dimensional plane, we can add up these two different things here. And here's a memorization trick. Notice how we're using the A vector so much more than the B vector. So what I like to remember is that this B vector here is only being used once each time you're trying to find one of these projections. And it's the same when you're trying to find a span, where here we're only using y twice here, or once in each operation. And so here is another ortho word. It's the orthogonal decomposition. And that's essentially just a way of writing everything that we just talked about. The y vector, which is given, is going to be equal to the projection of y onto W, or whatever the span is, plus the perpendicular of the projection of y onto W, which is essentially this part right here. And this makes sense. I mean, if we're looking at this is a triangle, this is a right triangle. And we know the Pythagorean theorem, which states, I'm just going to write it this way, c squared equals a squared plus b squared, where now this is a, this is b, and this is c. Now let's do an example here. So we have W, which is the span of these two vectors, and we want to find the orthogonal decomposition of this vector right here. So the first thing I like to do is to check if this span is indeed orthogonal. If it's not, we're going to have to use Gram-Schmidt, which we'll get into in the next example. Here I can see that 4 times 1 is 4, plus 1 times 0 is 0, plus negative 2 times 2 is negative 4, and that indeed equals 0. So we're good. I love to visualize this all the time by just drawing out a plane where this is W, and then kind of showing the projection here. So first we want to find this projection, and then we can find that one. I'll just write V1 and V2 here. Let's start with V1. So we're going to have 4, 1, negative 2. We're going to dot it with our vector here, negative 10, 18, 10. And then we're going to divide that by V1, just dot it with itself. And then V1 again. Look how many times V1 is being used. And I'm actually going to call that A just to show work here. Skipping over the math, I'm going to get negative 2 for this whole thing. And that is going to be equal to A. And so for B, we can do the same thing. So let's look at the second vector. V2, we have 1, 0, 2, and then we'll just dot it with negative 10, 18, 10, and then just use 1, 0, 2 the rest of the way. Now, I can do this in my head now, just because I've done quite a few, and I could just think, what's the double of 1? It's just 1. What's the double of 0? 0. What's the double of 2? It's 4. So we have 1 plus 4 equals 5. So our thing's going to be over 5. And I'll just throw in this 1, 0, 2 at the end, and that's going to be equal to B. So we get this as B. And now I'm just going to simplify A, and we're just going to do A plus B here. So that's going to be negative 8, negative 2, and 4, plus 2, 0, and 4, which is going to be equal to negative 6, negative 2, and 8. So okay, we have the projection. Now let's just get the perpendicular of that, and that's going to be simple. We just take the original and subtract it by what we just got at first. So it's going to be negative 10, 18, 10, minus negative 6, negative 2, and 8. This is the answer I got for that. And we can check if we dot this with negative 6, negative 2, and 8, what we should get is 0, because remember, when we dot two vectors that are orthogonal or perpendicular to each other, we should get 0. We get 24 minus 40 plus 16, which does indeed equal 0. So to finish off, let's just write out the orthogonal decomposition here. So negative 10, 18, 10, which is the original, is equal to negative 6, negative 2, negative 8, which is the projection, plus negative 4, 20, and 2. And obviously we could check this as well, like negative 6 minus 4 is negative 10, and it all works out. Now, like I mentioned before, if we don't have orthogonal vectors originally, we're going to have to use the Gram-Schmidt process to create those vectors. And I also like to think of this visually. So we have three vectors here, vectors 1, 2, and 3, and they're not orthogonal to each other. And so what we want to do is we want to take vectors 1 and 2 here, and we want to create this right here, which is going to be u2, which is just the perpendicular of the projection. And then now we create a span with what's now u1 and u2. We can just project, do the same thing, perpendicular projection to get u3. So we can continue just staring at this, or we can do an example. So we have these three vectors, which are basis for R3, and we want to find n orthogonal basis. Now, note, not the orthogonal basis, n orthogonal basis. So we can label this v1, v2, and v3. Now, v1 is just going to equal u1. We don't have to do anything there. So we have u1 is equal to 1, 1, 1. Now we want to find u2, and we can do that by projecting v2 onto u1. Once again, drawing out this image here. And we want to find this. Now, I'm just going to rewrite this to save time. Remember that what we're finding is going to be v2 minus the projection of v2 onto u1. So instead of having some adding thing and then subtracting, I'm just going to go straight and use this type of formula here. So we have 1, 2, 3 from our v2 up there minus the projection. So remember what that is. That's going to be 1, 1, 1 dotted with whatever we want to change, which is going to be 1, 2, 3. We're just going to have a bunch of ones here, and this is just going to be 3. It's going to be 1 plus 2 plus 3, which is 6 over 3, which is just 2. And this is just going to give us negative 1, 0, and 1. And what we'll notice is if we dot this with our u1, which is 1, 1, 1, we indeed do get 0. So we are doing well. It's always good to check these things. Just going to move the work up there as we find u3. So we have v3, which is going to be 3, 3, and 5. Now with this one, we're going to have to do the span now, which means we're going to have to do this process, but for two vectors. Once again, I'm going to rewrite this differently. So it's going to be 3, 3, 5 minus 1, 1, 1, dotted with 3, 3, 5. And then this, it's the same. And then remember, it's going to be minus here because essentially we're doing that a plus b operation, but all of it's negative. So that just becomes negative a minus b. I'm just going to label this as u2. With our u2, we are going to get this like so. And we end up with this garbage. Now, I have an 11 over 3 here, and while I can continue solving it, I don't want to deal with fractions at all. And mathematicians are lazy. So I'm going to do a trick, which is just taking out a 1/3. And when I take out the 1/3, then it's just going to be 11. But I'm going to have to take out the 1/3 out of everything. And so what times 1/3 is going to equal this just normal vector here? Well, it's going to be 3. So I can write it like this. Hopefully we can agree that this is equal to this. Simplifying it like that. All right, so now we have this. And the nice thing is we can actually just throw out this 1/3. We're looking at basis vectors here, and it really doesn't matter what the magnitude or like how long each vector is, specifically for the basis. So we can just throw that out. Once again, we can check if this is correct. So if I want to dot this with our original vectors 0 and 1 here, our u2, indeed we will get 0. And then we could check again with 1, 1, 1. And yes, we do get 0. I'm going to write in yellow now. So here's our u3, here's our u2, and here is our u1. And that is an orthogonal basis. All right, let's finally get into an application of this, which is least squares. So least squares, essentially, you have a bunch of data points, let's say, and you want to find some line that fits that data, all those points the best. So what you're going to be trying to find is these dots will create these squares. and you're trying to minimize the amount of area in these squares. It's a really weird way of putting it, but it's just saying what line can you create that has all the dots closest to that line, I guess. So this is quite useful when you're doing, tests and stuff here. So let's just say we are trying to test different diets, and we have two different diets, A and B. So we have 4 participants here. We have one which doesn't have any diet, the second one which is diet A, third which is diet B, and the fourth which is doing both. And we also have this error here that is important to include, but we're not going to get into because that's a whole thing on like linear models and a statistics concept. We can write this as a matrix as y1, y2, y3, y4 is equal to some matrix times A and B plus all of the errors. And this is simply 0, 0, 1, 0, 0, 1, 1, 1, which I'm just taking from this part right here. Now, this is probably the last formula you want to memorize. And the way I memorized this was I just said it a lot and I wrote it down a lot. It's going to be x is equal to A transpose A inverse A transpose Y. Just remember A, there's a lot of A's. A transpose A, all of that as an inverse, A transpose Y. I can't think of another way to memorize it. And essentially, this is just plugging in the numbers. Your A vector is going to be this right here, which is like, I guess, the tests. So x is going to be equal to, we're going to transpose this whole thing like that, multiply it with the original, and then all of that is going to be the inverse of it. And then we have the transpose again, and then we have y. So what is y? Well, when we get our test subject's results, we need the results to fit a line to. Let's just say that our results are 2, 0, -1, and 4. So now we could just throw this in there. And now we have to solve that. And I don't want to do that. If you've done this on your own, the answer should get you A is equal to 5/3 and B is equal to 2/3. So what does this actually mean? So this means for diet A, on average, people lost 5/3 pounds to that diet. And for diet B, they lost 2/3 of a pound. And congratulations, you now learned statistics and you now learned all of linear algebra. That was my entire semester of linear algebra. Like, this was literally my entire notebook. And just to finish the video off, I want to show the books that I threw at you in the beginning. This is the textbook that I used in class, Linear Algebra and Its Applications by Lay. Just a standard textbook. I'm pretty sure I covered quite a bit in here, but there's some more reference that's really useful. This one is also same name, but it's by Strang. This one's really dense. It's got like calculus, differential equations, and whatnot. And then finally we have like the fun read, which is the manga guide to linear algebra. And I took some explanations from this book actually to make this video. I think it's just a fun read, especially once you've kind of gone through everything. So with that, thanks for watching and good luck on finals.